Swayam Prabha. Digital India. Educated India.
Welcome to lesson 4.3 Traffic Loading Part 2. This is the third lecture in Payment Design module. In the last lesson, which was on Traffic Loading Part 1, we have discussed various parameters of traffic loading that need to be considered for payment design, which included the loading, which also included the transverse distribution of wheel loads. We would also discussed about various types of vehicles that we have to consider, big vehicles, small vehicles, which carry heavier loads and small loads, and other features of traffic loading parameters we discussed. Last class we did not specifically discuss about certain aspect, which is on how to take into account the different loads that are carried by vehicles. Besides this, we will also consider certain other aspects that are very important for payment design. The specific instructional objectives of this lesson would be, after completing this lesson, the student is expected to be familiar with the procedures for converting a given multi-wheel load system consisting of 2 wheels, more than 2 wheels, number of axles, how to convert all those number of wheels into an equivalent single wheel load. We will also try to learn the concept of the relative damaging effect of axle loads, and using this concept, how different number of repetitions of different magnitudes of loads can be converted into an equivalent number of a standard load. So, we would be discussing about two different concepts mostly in this: how to convert a given wheel load configuration into an equivalent wheel load, single wheel load that is, or how to convert different number of repetitions of different load magnitudes into an equivalent number of repetitions of a standard load. We will also be discussing about the approaches that are normally adopted taking into account the traffic design and payment design. There are 3-4 approaches are there. We will also be discussing those approaches. Normally, traffic load is considered in design in different ways. We understand that payments of highways or airports or other types of roads carry different types of vehicles. This we discussed in the previous lesson, and these vehicles, which are different in shape and size, carry different magnitudes of loads, and these loads occur repeatedly. Some facilities carry more number of repetitions during its service life period, some carry lesser number of loads, some of these facilities carry very heavy loads, some carry loads of lesser magnitudes. How do we take these variations into account while designing payments? We understand there are going to be repetitions of loads. We also understand that the loads are of different magnitude. So, how do we account for all these things and come out with one single number or one single load which can be used and input in payment design? Which vehicle has to be designed, or how many number of repetitions of a standard load we have to design the payment for? These are the issues that we are going to discuss in this lesson. Load consideration payment design are usually adopted in as per three different approaches. First one is fixed traffic approach, then we have fixed vehicle approach, then the third approach is variable traffic, variable vehicle approach. Let us take up each one of these approaches one by one and discuss them. In the fixed traffic approach, the heaviest anticipated vehicle is of importance for us. This is our main concern. The number of repetitions that a given facility gets is of not that significance compared to the load that the heaviest vehicle is going to carry. We are very seriously concerned about the load that the biggest vehicle or heaviest vehicle is going to be applying on the pavement. Naturally, these are facilities where the number of repetitions are not that significantly high. For example, when we talk about airport payments, airports can have vehicles which would whose magnitudes of loads would be varying very significantly. There can be very heavy vehicle, there can be smaller vehicles. The number of repetitions are not of the order of millions like you have in the case of highway payments. So, numbers of repetitions are not very significant, but the load is very significant in this case. So, the payments are designed for a single wheel load. We are not going to take the entire configuration because the heaviest vehicle will have certain configuration in terms of the number of axles it is going to have and in terms of the number of wheels it is going to have on each axle. All these configurations, whatever be the configuration, number of axles, number of wheels, will have to be converted into a single load, equivalent single load, equivalent being that it would produce a similar damaging effect on the pavement as would be produced by the total vehicle. So, we will be talking about an equivalent single wheel load, and that is the input parameter that we will use for designing payments for these facilities where heaviest vehicle is of concern for us. As I indicated, multiple wheels that a vehicle has got of different configurations will be converted into an equivalent single wheel load, ESWL. This is commonly used for design of airport payments and for highway payments and other roads which would carry very heavy loads, but it will have less traffic volumes. But nowadays this is not a very commonly used approach. On the other hand, in the fixed vehicle approach for design of payments, the design is governed by the number of repetitions of a standard vehicle. Here we will talk about a standard vehicle, and then how many repetitions of a standard vehicle the payment is supposed to carry. That number is going to be the input parameter for payment design. But we understand that there are going to be different magnitudes of loads, different types of vehicles, and each type of vehicle may have different repetitions during the service life period. During the 20 years of life period or 15 years of life period of a given payment, 10 ton axles may be certain number, 8 ton axles may be a different number, 6 ton axle may be different number. All these weights, all these numbers will have to be converted into a equivalent number of repetitions of a standard load. The most commonly used, or rather the standard load that is considered is a 18,000 pound single axle load, that is 80 kilonewton load single axle load is considered to be the standard axle load. All the vehicles, all the axle loads that a payment is expected to carry, expected to receive during its design life period will be converted into equivalent repetitions of 80 kilonewton single axle load repetitions. Axles that are neither single nor equal to 80 kilonewton will be converted into equivalent standard axle loads using equivalent axle load factors. These are conversion factors that will use to convert a given load into an equivalent repetitions of the standard load, which is 80 kilonewton. In this, we multiply the repetitions of a given axle load by the equivalent axle load factor corresponding to that particular load, and this will give us the equivalent number of 80 kilonewton axle load repetitions. But we have to have some information about what is the equivalent load factor that we have to use or equivalent axial load factor that we have to use to convert a given load into equivalent repetitions of a standard load. The sum of all these equivalent repetitions obtained for all the axial loads anticipated to be coming during the design life period is used as the design life period. This number of equivalent standard axles is the design input for design. Most of the design approaches follow this method of considering payment traffic in payment design. We can also have an approach which is called as variable vehicle variable traffic approach, in which we will not talk about a fixed vehicle, we will not talk about a standard load, we will not talk about standard traffic level also. Rather, whatever be the load, whatever be the number of corresponding repetitions, we will take into account all of that. If you have 10,000 repetitions of 10-ton axle, we will find out what is the damage caused by 10,000 repetitions of 10-ton axles and certain other repetitions of 8-ton axle, and then maybe another 30,000 repetitions of 6-ton axle. We will take into account all the loads and all the corresponding repetitions. We will not talk about anything fixed here. So, there is no need to deal traffic either in terms of equivalent standard wheel load or equivalent standard axle load. Such an approach is normally used with procedures where we calculate the cumulative damage of the payment caused by individual loads and the corresponding numbers, such as design approaches where we are trying to calculate cumulative fatigue damage or accumulated permanent deformation. Such approaches we can use this, but still this is also not a very common approach. Coming to the fixed traffic approach, where we are having to convert a given vehicle into an equivalent single wheel load. You may have two wheels, we may be talking about a dual wheel set which needs to be converted into an equivalent single wheel load, or we may be talking about 4 different wheel loads which has to be converted into an equivalent single wheel load. So, there has to be some definition of what is equivalence and then how that has to be calculated. There are various approaches that are followed. Equivalent single wheel load is defined as the load on a single tire or single wheel that will cause an equal magnitude, that is where the equivalence is coming to picture, of a pre-selected parameter. Equivalence in terms of a pre-selected parameter, either stress, strain, deflection or some other distress at a given location within a specified payment system, to that resulting from a multiple wheel load at the same location within the same payment system. So, we are trying to compare two different situations. We have the effect produced by a single wheel load, that is equivalent single wheel load in a given payment system at a given location. The equivalent effect is in terms of the deflection that is produced, stress that is produced, or it can be strain. We will have to select one of these parameters. Different agencies select different parameters, and we are also talking about a particular payment system and the parameter is calculated at a particular location in the payment. So, these are all fixed. So, individual agencies define equivalent single wheel load using different framework of what is the payment system that is considered, what is the location at which this parameter is calculated, and what is the parameter we are calculating. So, equivalence is in terms of a selected parameter for a selected payment at a selected location. The parameters of equivalence can be, as I just indicated, some of them: equal vertical stress. Equivalent single wheel load will have to produce same magnitude of vertical stress as would be produced by a set of wheel loads. It may be in terms of equal vertical deflection, it can be in terms of equal tensile strain, equal contact pressure, equal contact radius. These parameters can be theoretically be calculated using some appropriate theory, or they can be experimentally be determined as specified by the design methodology. So, any design methodology which uses an equivalent single wheel load approach has to specify how this equivalent single wheel load has to be determined, whether it has to be determined by an experimental approach. If it is an experimental approach, what sort of an experiment has to be conducted, how exactly this has to be done, and if it is a theoretical one, which theory is to be used, at what location, which parameter has to be calculated. Complete framework has to be specified by the agency which is using this equivalent single wheel load approach. The first concept that we will use to determine equivalent single wheel load is equal vertical stress concept. So, here we are referring to equal vertical stress that is produced by, right now that we are seeing here is a dual wheel set. You have two wheel loads applied on a pavement system. Each wheel load carries PD as the load. And the clear spacing between these two wheels is D, and the center to center spacing between these two wheels is SD. If you see from this diagram, if you make some simplification about the load distribution through this pavement, stress distribution through the pavement, at a depth of d by 2, these two envelopes just start getting overlapped. The stress envelopes produced by the two individual wheel loads just start getting overlap, and then at a significantly larger depth, which is approximately equal to twice SD. The suffix D is normally used because we normally refer to dual wheel sets and its conversion into equivalent single wheel load, but that is not exactly required. So, at a depth of 2 SD or beyond, the overlap is of such significant magnitude to such an extent, we can consider the stress produced at any given location within this overlap zone will be equal to that of the loads that is the stress that is produced by PD left side wheel and the right side wheel combined together. Let us see how this concept can be used to compute equivalent single wheel load. We are referring to equal maximum subgrade vertical stress. If we have a two layer system, we are talking about the vertical stress on top of subgrade. If we have single layer system where there is no pavement, it is only subgrade that we are talking about. Normally such systems are not of much importance to us, but still if we are referring to a single layer system, we are referring to vertical stress at a specified depth. This is based on the approximation of stress distribution in the layer system or single layer system. For a pavement thickness less than d by 2, if you have a pavement of thickness less than d by 2, as we have seen in the previous slide, there is no overlap. Hence, the equivalent single wheel load will be PD, that is equal to one single wheel load. The other wheel load is not coming to picture, its influence is not to be seen at smaller depths. At depths of approximately 2 SD or greater, the effect of overlap is such that it is equivalent to the stress caused by 2 PD, twice the magnitude of each one of these wheel loads. But for intermediate depths, a linear interpolation is made between the load and the thickness plotted on a log-log scale. Let us see this in the next slide. This concept is presented pictorially here. On the x axis we have the thickness plotted on a log scale. On the y axis the corresponding equivalent single wheel load is plotted. As you can see here, for depths less than d by 2, the equivalent single wheel load will be PD. For depths more than or equal to 2 SD, the equivalent single wheel load would be 2 PD, and for any intermediate depth given by Z, the corresponding equivalent single wheel load P can be obtained by interpolation. The expression for this is given here. Log equivalent single wheel load is equal to log PD, this is one single wheel load of the dual wheel system, plus 0.301 log twice depth divide by d, small d is the clear distance between the wheel loads, divide by log of 4 st, st is the center to center spacing between the wheel loads, divide by the clear spacing between the wheel loads. Let us take an example and then calculate the equivalent single wheel load. What we have here is a dual wheel system, each wheel carrying 20 kilonewton. The center to center spacing between these two wheels is 300 millimeters, and the radius of contact area, assuming that these are circular contact areas, is 100 millimeter. So this will give us PD equal to 20 kilonewton, SD equal to 300 millimeters, and then D will be equal to 300 minus 100 minus 100, that will be 100 millimeters. And the depth that we are specifying is 200 millimeter, so Z is equal to 200. Let us see the calculations. And this is how we assume this stress distribution is going to be. So at a depth of less than 50 millimeter, that is d by 2, there is no overlap. So the equivalent single wheel load is going to be 20 kilonewton. At a depth of 600 millimeters, that is twice ST, that is 2 into 300. There is going to be complete overlap. So within this region, the equivalent single wheel load will have to be 2 into 20 kilonewton, that will be 40 kilonewton. But in between, at a depth of 200 millimeter, at which we are interested in, the equivalent single wheel load has to be somewhere between 20 kilonewton and 40 kilonewton. So this we can see from this plot. For 50 kilonewton, 50 millimeter depth, 20 is the equivalent single wheel load. For 600 millimeter depth, 40 is the equivalent single wheel load. But for 200 millimeter depth, plotted in a log scale, we can directly obtain what is this thickness. Let us see if we can calculate this. So log of equivalent single wheel load will be equal to log 20 using the expression that we have given in the previous slide, plus 0.301 log 2 into 200 by 200 is the depth by log 4 into 300 by 200. Solving this, we will get an equivalent single wheel load of 34.2 kilonewton. This could have been obtained graphically also. We can also adopt equal vertical deflection concept. In this approach, single wheel having the same contact radius as one of the dual wheels or as one of the multiple wheels that are there, and resulting in a maximum deflection equal to that caused by multiple wheels. So we are trying to equate the deflection, we are trying to equate the maximum deflection produced by equivalent single wheel load and produced by a given set of wheel loads. Some approaches also use equal contact pressure. Here we are trying to keep the contact radius or contact area of the equivalent single wheel load equal to that of one single wheel load of the given loading system. Normally we calculate the deflection at the interface of a pavement or at a specified depth in the pavement system if it is only single layer system. So if it is a single layer system, we calculate the deflection at a specified depth. If it is a pavement and they subgrade a two layer system, the deflection will be calculated at the interface. There are number of methods available for working out these parameters. If it is a single layer system, we will use what is known as a elastic half space analysis. We will be discussing these things in greater detail when we talk about analysis of payments, but at this stage we will just use some charts or some method that is available for calculating these things. And we also have two layer systems for which we can calculate interlayer deflections. Standard charts are available. If we have computer programs, we can calculate any of these things. This is depicted here. We have a two wheel system here separated by spacing S, each load being P and load rates being small a. This is a two layer system which is characterized by its Poisson ratio value and the modulus value. Modulus values are E1, E2 for the two layers, M1 and M2 represent the Poisson ratio value for both the layers. So what we are trying to identify for the given loading system, which is given on the left hand side, is to find out where the maximum deflection would be at the interface, which is at a depth of h. So maximum deflection on the interface, we have to explore different locations. Obviously it has to be somewhere from the center line of one of the wheel loads and at the axis of symmetry of both the wheel loads. So we explore different points, calculate the deflection, find out where the maximum deflection is going to be, and similarly to obtain the equivalent single wheel load, we will keep the radius of this equivalent single load constant are equal to that of the radius of contact of one of these wheel loads. We keep the same parameters, and at this depth obviously the maximum deflection is going to be along the axis of symmetry at the interface. So we will try to calculate this and we will try to work out where the maximum deflection is going to be for the system that is there on the left hand side. Then the wheel load that will produce the same amount of maximum deflection corresponding to the left hand side system will be the equivalent single wheel load. For a single layer system, the deflection is usually a function of the contact stress, radius of contact area, and a function of the modulus value of the system multiplied by a factor f, which is called as deflection factor, where d is the deflection at depth z and the radial distance r, which is measured from the center of the load, and E is the elastic modulus value of the payment, subgrade modulus value in case of a two layer system, and F is the deflection factor, which is a function of the position of the wheel, position of the point at which we are trying to calculate the deflection. R is the radial distance from the center of the load, Z is measured from the payment surface. We have charts of this type available for computing vertical deflection factors as a function of depth expressed as the ratio of Z by, this is the radius of load contact area, and also as a function of radial distance at which, if this is the location at which we are trying to calculate the deflection, so we are referring to this radial distance and this depth expressed as r by a and z by a, where a is the radius of load contact area. So if we know the location, we know r, we know z expressed as r by a and z by a, then for a given z by a and r by a, we can get the corresponding f value. Once we get the f value, we can substitute this in the previous expression. If we know the modulus value of this material, if we know P, the pressure, and then A, we can calculate the deflection. So as you can see here, deflection produced by an equivalent single wheel load is equal to the pressure of equivalent single wheel load, load radius, that is PA, load radius which is nothing but equal to the load radius of the any one of those loads that are there in the given system, and then deflection factor that is applicable for the equivalent single wheel load, and then modulus value of the subgrade. For the multiple system, we have to get the tire pressure corresponding to the multiple system. This is given, this is known to us, and we also know the radius of contact area. We have to obtain what is the maximum deflection factor for the number of loads that we have, and also where the maximum deflection is going to be. This we have to obtain. This is also known. So for equivalence concept, this has to be equal to this. The deflection produced by equivalent single wheel load has to be equal to deflection produced by multiple wheel loads. That means pressure for equivalent single wheel load multiplied by the load deflection factor for equivalent single wheel load will be equal to pressure corresponding to multiple wheel load, and then maximum deflection factor which correspond to the maximum deflection produced by the given load system. This is known, P multiple is known. F maximum is a function of the wheel load configuration, that is with reference to any one single wheel load, where the R and Z are for the points at which we are exploring to find out the maximum deflection. F equivalent single wheel load is a function of H, and obviously we are referring to R equal to 0 because maximum deflection is going to be produced along the axis of symmetry. So R is 0, but we have to see what is the depth at which we are referring to, then the corresponding factor has to be selected. So this way P equivalent single wheel load and the corresponding equivalent single wheel load can be obtained. Once you get this, from this and the load contact area, we can calculate equivalent single wheel load. For a two-layer system also we can adopt similar concept. Here also we use the same approach. The deflection is a function of pressure, load contact area, rather the radius of load contact area, deflection factor, and the subgrade modulus value, where F is the interface deflection, because if it is a two-layer system we are interested in the deflection that occurs at interface. So F is the interface deflection factor, which is a function of, like in the previous case, the radial distance and the pavement thickness, which defines the location of the interface. So we have a similar chart available for interface deflection factor. Given by F, which is a function of the radial distance R and the thickness of the pavement, which defines the interface location. You normally get standard charts in standard literature for various charts available for different modular ratios, where E1 is the modulus value of the upper layer, E2 is the modulus value of the lower layer. For any given ratio you can get a set of chart for this. So once you identify the chart that has to be used, you know the radius at which this has to be calculated, and also the thickness of the pavement which defines the interface location. We can identify the interface deflection factor. So following the same approach that we used earlier, equivalent single wheel load is P equivalent single wheel load, A deflection factor for equivalent single wheel load, and then modulus value. D multiple deflection produced by multiple wheel loads is pressure multiple radius of load contact area. The deflection factor that corresponds to the maximum deflection produced by all those wheel loads, modulus value of the subgrade. Equating these two, we will get this pressure multiplied by deflection factor for both the systems. Like in the earlier case, we know multiple system P, F maximum has to be evaluated for the given configuration. F equivalent single wheel load is a function of thickness, since R is 0. Once we get this value, we can calculate the corresponding equivalent single wheel load. Here is an example. We are trying to work out equivalent single wheel load for a dual wheel load system, 20 kilonewton each, separated by 300 millimeter center to center spacing. A is 100 millimeter. The modulus value of the first layer is 250 megapascals, modulus value of the second layer is 50, Poisson ratio values of both the layers is taken as 0.5, interface is at a depth of 200 millimeters, that is thickness of the pavement is 200 millimeters. For this, how we proceed is, for the given loading system, we explore different locations starting from point 1, point 2, point 3, we can explore more points also. So, find out what is the deflection at this location, what is the deflection at this location, or alternately we will try to find out what is the deflection factor, because once you know deflection factor, PA deflection factor divided by modulus value of the subgrade, other things being constant, deflection is basically a function of F. So, for point 1, for load A, radius is 0, so R by A is 0, Z by A is 2, that is 200 by 100, that is 2. So, the deflection factor corresponding to this load at this point can be obtained using the chart. We know R by A, Z by A. Similarly, the deflection that is produced at this location by load B can also be worked out by the corresponding radial distance and the depth for this point, and for this load the radial distance is 300 millimeter. So, that is 300 by 100, that is 3. Z by is same ratio as we have here. So, for this the deflection factor as seen from the previous chart is 0.28, in this case it was 0.5. So, the total deflection factor which is influenced by both these wheel loads at this point is 0.5 plus 0.28, that is 0.78. Similarly, for point 2, R by A is 1, Z by A is 2, because the radial distance is 100, A is 100, so R by A is 1, Z is 200, A is 100, Z by A is 2. So, this deflection factor is 0.45. The deflection factor due to B can also be similarly obtained, R by A is 2, Z by A is 2, deflection factor is 0.36. So, the total deflection factor is 0.45 plus 0.36, that is 0.81. We can also similarly explore point 3. So, for both load A and B, the deflection factor can be obtained as 0.4 because of symmetry. So, the total factor here is 0.3. So, out of the 3 locations that were explored to identify where the maximum deflection is going to be on the interface, you can see point 2 gives a deflection factor of 0.81. Possibly there could have been another point where, if you can explore it further, which would have been slightly larger than this 0.81 value. Anyway, assuming that this is the location where maximum deflection is going to be, so we will find out the corresponding equivalent single wheel load to produce similar deflection at that location. So, P multiple is given as 20,000 by this is the radius. So, this is the pressure for the given system, 20 kilonewton is the radius of contact is given. So, we can calculate the tire pressure. So, P equivalent single wheel load multiplied by factor of equivalent single wheel load is equal to P multiple into F maximum. F maximum we already worked out as 0.81, pressure is 0.6364 that we have calculated. F equivalent single wheel load will be, for a given single wheel load, R equal to 0, Z by A is 2, for this F will be 0.5. So, this is also determined. So, we only need to determine what is the tire pressure corresponding to equivalent single wheel load. This, from this expression you can calculate it as 1.031. Once we have the tire pressure corresponding to equivalent single wheel load, we can calculate the equivalent single wheel load tire pressure multiplied with the area of contact area, load contact area, since we know the radius of load contact. Okay. So, this gives us 32.4 kilonewton. There are various other concepts also that can be utilized for working out equivalent single wheel loads. We have seen equal vertical stress, we have also seen equal vertical deflection at a certain depth or at the interface. We can also use equal tensile strain, equal tensile stress, or other concepts also can be used. If you are using fixed vehicle concept, wherein we are talking about a fixed vehicle and converting the reputations of all other vehicles into an equivalent number of reputations of the fixed vehicle, we are going to make use of equivalent axle load factors. In some design methods, payments are designed for a selected number of reputations, as we discussed earlier. The standard load that is considered is 80 kilonewton. Equivalent axle load factors are used to convert different axle loads into equivalent reputations of standard axle. Equivalent axle load factor defines the damage caused to the payment by one application of the axle load under consideration, 100 kilonewton or 120 kilonewton, relative to the damage caused by a single application of a standard axle, which is 80 kilonewton. So the damage caused to the payment by different axle loads is compared and equivalent axle load factors are worked out. If you know the equivalent axle load factors for different load groups, if we have that information, so the design would be based on the total number of applications of standard axle load during the design period, given as total number of equivalent standard axle loads will be sum of axle load factor, equivalent axle load factor corresponding to ith load group and the number of repetitions of the ith load group. For designing payments, it is necessary to have information on the equivalent load factors for any particular load group that we want to convert into equivalent standard axles, and we also need to have the expected axle load spectrum over the next 20 years or 15 years. How many repetitions of certain load group, 0 to 5 kilonewton, how many repetitions, 5 to 10 kilonewton, how many repetitions, 10 to 15, how many. This information is required. Somebody has to make projections about this, and we also have to have equivalent load factors so that we can convert each one of these load groups into equivalent standard axle load repetitions. The axle load spectrum is nothing but number of passes of axles for different load groups, and equivalent axle load factor is a function of, we cannot have the same equivalent load factor for a given load. For example, if we are talking about 100 kilonewton, we will not have exactly the same equivalent load factor for all situations. It is a function of the type of payment that we are referring to, its composition, strength, and also the criterion that we are using to define performance of the payment. Equivalent axle load factors are usually determined by conducting axle load surveys in the field, or rather by observing the relative damage caused by different axle load groups to a given specified payment system. The equal load factors obtained from Ashore road test are most commonly used by almost all the agencies. Ashore road test, we have referred to this earlier, which was conducted in the 1950s and 60s. So this was one of the concepts that has evolved out of Ashore road test. Equivalent axle load factors can also be obtained from theoretical exercise using appropriate mechanistic criteria. Equivalent axle load factors are different for different types of payment, as I indicated in the previous slide. Equivalent axle load factors are a function of payment type, the approach that we use for defining performance. The Ashore equivalent load factors have been derived out of large number of experiments that were conducted on different types of payments, by loading these payments with different load magnitudes, and by observing the performance of these payments, the damage that is caused to these payments by different load magnitudes. So these are usually found in tabulated form for different types of payments, different load magnitude, different equivalent standard axle load factors are available, but a simplification of this is what is known as the fourth power law, which is given as equivalent standard axle load factor is axle load under consideration divided by the standard axle load, which is 80 kilonewton, to the power 4. That is why it is called as fourth power law. This is an approximate one. For example, if we are referring to 160 kilonewton load and we are trying to convert that into equivalent number of 80 kilonewton standard axle. So, the conversion factor will be, or rather the equivalent standard axle load factor will be 160 by 80 to the power 4, that is equal to 16. This means that a 160 kilonewton axle is capable of producing about 16 times more damage compared to a 80 kilonewton axle. So, this way you can obtain equivalent standard axle load factors for different load groups, only we have to use the fourth power law. The ASHO equivalent axle load factors, as you can see in various standard literature, are given as for different axle load groups. Each axle load group is given in terms of kips, 1000 pounds. For example, 18 kilonewton, 18,000 pounds is the standard axle. Okay. So, corresponding to this, you will have equivalence factor to be 1. If you consider 40,000 pounds axle load, so this should approximately correspond to 40 by 18 to the power 4. So, this would be approximately equal to 39.57, but this is more precise value as obtained in the ASHO road test. But this is for a pavement whose terminal condition is defined in terms of a terminal serviceability index value of 2. We will not discuss this right now, but this is for a specified definition of serviceability, and for different types of pavements defined by what is known as structural number. More the structural number, stronger is the pavement. So, for different types of structural numbers, you have different equivalent standard axle load factors. So, we cannot have for all types of pavements and for all types of performance definitions, we cannot have the same equivalent axle load factor. We will have similar factors available for concrete pavements. In this case, instead of the structural number, the strength of the pavement is represented in terms of the slab thickness, in terms of inches 6, 7, 8, 9, 10 and so on. Again, this is specified for a particular terminal condition of the pavement defined as PT equal to 2. Similar tables are available for different other serviceability terminal serviceability values 2.5, 3 and so on. So, in order to be able to convert given axle load spectrum into equivalent number of standard axles, we need to have information about the axle load spectrum that is going to be there during the design life period. For this, we have to carry out axle load survey. Axle load survey is nothing but measurement of axle loads on a sample basis of all the commercial vehicles, or rather a sample of commercial vehicles that are plying on a given facility. If there is a new road, so we cannot naturally collect samples on this particular road. We will collect data on similar facility which can be considered to be applicable to this facility also when it is constructed, and this data is collected using portable weigh pads, because we cannot expect the vehicles to be taken to a weigh bridge at a standard location, fixed location. So, what we have to use are portable weigh pads which can be placed on the road, and you can stop the vehicles, measure each one of these wheels, and from that you can collect axle load information. This photograph here shows a portable weigh pad that was developed by IIT Kharagpur. A improved version of this is presently available in a commercial form. You can see the wheel load placed on the weigh pad. On either side you have wooden ramps facilitating the vehicle to climb on that. What we do in this survey is we select a sample. We will not normally stop all the commercial vehicles. We are only trying to take the weights of commercial vehicle. This we have discussed in the previous lesson. We are interested, as far as the pavement disease is concerned, only in commercial vehicles, because other smaller vehicles will not be able to produce significant damage to the pavement. Adequate sample has to be selected. Usually only wheel loads are measured, normally complete axle is not measured, but if you put two pads on either side, you can measure the complete axle simultaneously. If you are measuring only wheel load, we assume the axle load to be approximately equal to twice the wheel load that is measured, and commercial axles normally in both directions are monitored. So, if you have data collected like this, having load group of 0 to 40 kilonewton, this is the frequency, 40 to 80 kilonewton, this is the frequency, 80 to 120, this is the frequency, and the midpoint of this is 20. This is the equivalent axle load factor, 20 divided by 80 to the power 4, this would be the equivalent axle load factor. Then equivalent number of standard axles, if you have 50 axles ranging from 0 to 40 kilonewtons, these 50 axles would be equivalent to 3.13 numbers of 80 kilonewton axles. Similarly, 160 to 200 load range group, if you have 40 axles, the midpoint of this will be 180, equivalent axle load factor will be 25.629, 180 divided by 80 to the power 4, and this multiplied by 40, this is the equivalent number of 80 kilonewton standard axle loads. So, that is the equivalence of 40 numbers of loads ranging between 160 to 200. So, similarly we can work out equivalent standard axles for each one of these load groups, knowing the frequency for each load group. As you can see, the total of these axles that have been measured is about 1000. So, these 1000 axles are equivalent to, if you take a sum of this is equivalent to 5000.6 standard axles. That means one axle is equal to approximately about 5 standard axles. We have measured about 450 commercial vehicles, they had about 1000 axles, because some of the vehicles had more than 2 axles. So, 450 commercial vehicles are equal to 5000 standard axles. That means one commercial vehicle is equivalent to 5000 divided by 450, that is 11.11. This is called as vehicle damage factor, which is a representative parameter that will give us one commercial vehicle is approximately equal to so many standard axles. So, that means vehicle damage factor, if you have this information with you for a given road, this is the vehicle damage factor to be adopted. Then if you know what are the commercial vehicles that are going to be there, that multiplied by this vehicle damage factor will give us equivalent number of standard axles. So, this is how we can obtain the vehicle damage factor by conducting a axle load survey, by knowing the number of commercial vehicles that were sampled, by converting all of them into equivalent number of standard axles. Okay. So, this were discussed. This, if we can get information on vehicle damage factor, which can be determined by conducting axle load surveys, we can convert the commercial vehicles into equivalent number of standard axles. We also take into account the speed also at times into consideration. This is important for selecting appropriate metal properties at any given location on the pavement. If the load is away, the stress is 0. As the load approaches this location, stress builds up, reaches a maximum. As the load moves away, stress becomes 0 again. So, this is how the stress builds up. So, the points that are closer to the surface will have higher stresses, but smaller loading time, whereas these points that are at lower depths will have much larger loading times, but smaller magnitude of stress. This concept again we will discuss when we talk about characterization of pavement materials. So, estimating design traffic, we have discussed this partly in the previous lecture. We need to start with initial traffic, we have to have information on vehicle damage factor, we also have to have lateral placement characteristics. Using this information, we can calculate what will be the total number of standard axles that are expected during the design life period of 20, 15, 25 years. For example, if you take a design life of 15 years and a traffic growth rate of 8%, VDF of 4.5, and if it is a 6 lane road, divided facility, as we have seen in the earlier case, we are using a distribution factor of 0.6. So, we can work out the number of equivalent standard axle load repetitions as 160.55 In this case, we have also used a vehicle damage factor of 4.5. To summarize, in this lesson we have discussed about fixed vehicle, fixed traffic, variable traffic and variable vehicle approaches. We also learnt about computation of equivalent single wheel load from different consideration. We also discussed about equivalent standard axle load factors for converting the repetitions of a given axle load into equivalent repetitions of standard axle, and also learnt about vehicle damage factor and how that can be used to convert a given volume of commercial traffic into equivalent cumulative standard axle load repetitions. We also discussed about axle load surveys or wheel load surveys that can be conducted, and also about the importance of considering lateral placement characteristics of wheel loads of commercial vehicles, and we have seen how using all this information equivalent number of standard axle loads can be estimated for a design life period. Let us see some questions that we would like to be answered. We will provide the answers for this in the next class. Explain the concept of fixed traffic, fixed vehicle and variable traffic approaches for pavement design. Second one is 100 repetitions of 140 kilonewton axle load is equivalent to how many standard axle load repetitions. Third is estimate the design traffic using the following data. There is a 2-lane road, average daily traffic is 4,000 commercial vehicles per day, two-way traffic, vehicle damage factor is 5, design life is 15 years and rate of growth of commercial traffic is 7%. Answers for questions that we asked in the previous lesson is: what are commercial vehicles? Why do we consider only these for pavement design? Commercial vehicles are those which have a laden weight of more than 3 ton, because smaller than these vehicles which carry smaller loads do not produce significant amount of stresses so as to cause significant damage to the pavement. That is why we would not consider other than commercial vehicles. What is the legally permissible gross weight for a vehicle having 2 axles? Front axle has got single wheels and rear axle has got dual wheels. As you have seen in the previous lesson, if a axle has got single wheels on either end, permissible limit is 6 tons, and if a axle has got dual wheel set on either end, permissible limit is 10.2 ton. So therefore, in this case 6 plus 10.2, 16.2 tons is the permissible limit. Next, show the different typical load contact shapes that can be considered for a single wheel load of 20 kilonewton and tire pressure of 0.6. I am sure this you will be in a position to calculate. You have the load given, you have the contact pressure given. If it is assumed to be circular contact area, 20,000 divided by 0.6, that would give the area, and you can calculate the load radius. Similarly, you can calculate other shapes that were discussed in the earlier step. For a 6-lane divided highway carrying total two-way volume of 8,000 commercial vehicles per day with 50-50 directional split, what is the design daily traffic? So we have a divided carriageway, it is a 50-50 directional split. So in one direction we will have 4,000 commercial vehicles per day. Since we have 3 lanes in each direction, if you refer to the previous lesson, we have said 60% of the traffic in this direction has to be taken if it is a 3-lane separate carriageway that we have. So this becomes 4,000 into 0.6, that is equal to 2,400 commercial vehicles per day. That is the traffic that we have to consider in this direction. Of course, that we have to adjust this for using appropriate vehicle damage factor and then convert this into equivalent standard axle load repetitions. That in fact is the input that we are going to use for pavement design. That comes with this, we come to the close of this lesson. So thank you.